Hey guys, how are you doing? In this video we will discuss the theory behind the extreme values of a function, so its maxima and its minima. In the next video I will show you some example and I will put a link into the description for it. But now, grab your pen and paper and I will see you in a minute. Let's first look at a simple function x cubed over 3 minus x. It looks like that at the point minus 1, the values of the function f of minus 1 is bigger than or equal than the value of f of x for all of x between minus 2 and 0. Let's zoom into that interval. Before minus 1, the function is increasing, and after is decreasing. Do you remember the connection between monotonicity and derivative? Let's have a look. The function is increasing before minus 1, and its derivative is positive. At minus 1, the derivative is exactly 0, and at this point the function reaches its maxima, and then the function is decreasing and the derivative is negative. This example tells us the following. Consider f of x differentiable. If there exists a point x0 such that the derivative of f at this point is equal to 0, and the derivative change sign at x0 from positive to negative, then f of x has a local maximum at x0. But now, let's go back to our function. It looks like that at point 1, the value of f of 1 is less than or equal than the value of f of x for all x between 0 and 2. Let's zoom in that interval. Before 1, the function is decreasing, and after is increasing. The opposite as before. Let's now look again at the behavior of the derivative. The function is decreasing before 1, and its derivative is negative. At 1, the derivative is exactly 0, which is the point where the function has its minimum, and then the function increases and the derivative is positive. This example tells us the following. Consider f of x differentiable. If there exists a point x0 such that the derivative of f at the point x0 is equal to 0, and f prime change sign at x0 from negative to positive, then f of x has a local minimum at x0. From what we observed, we can formulate the following strategy to find local maxima and local minima for a function f of x. First, we have to compute the derivative, f prime of x. Then, we have to find its critical point, which are the point where f prime of x is equal to 0. Then, we have to compute the sign chart of f prime of x. And based on wherever f prime of x change sign or not at some point, we can conclude if these critical points are local maxima, local minima of neither of the two. For example and exercises, well, we just have to wait for the next video. Let's now consider a parabola of the form f of x equal to a times x minus x0 squared. We can plot the value of this function for several a and x0, and you will notice that if a is positive, then the parabola has a minimum at the point x0. Instead, if a is negative, then the parabola has a maximum at x0. But why this is so important? Let's go back to our function and zoom around the local maximum, which is the point x equal to minus 1. If we plot the function g of x equal to f second of minus 1 times x plus 1 squared plus f of minus 1, it approximates really well the function f of x nearby the point minus 1. And both of them had a maximum at that point. Furthermore, we can compute the second derivative of f at minus 1, which is equal to minus 2, which is negative. We can do the same things around the local minimum, and we can plot again the function g of x equal to f second of 1 times x minus 1 squared plus f of 1. And again, this function approximates really well f of x nearby the point 1. And both of them has a minimum at the point 1. As before, we can compute the value of the second derivative of f at the point 1, which turns out to be equal to 2, which is positive. What we've seen is at the essence of the second derivative test for local extrema. In particular, we discovered that if a function f of x is such that f second exists nearby a critical point x0, which means that the first derivative of f at that point is equal to 0. If the second derivative at the same point is bigger than 0, then the function f of x has a local minimum at x0. If the second derivative is negative at the point, then the function has a local maximum at x0, and if the second derivative at that point is equal to 0, well, the test is inconclusive. The function can have both a maxima or a minima at that point. This is all the theory I have for you for today. For the exercise, you have to wait for the next one, but be kind and leave a like, and I'll see you next time.